Okay, so now we are actually going to calculate the amounts of weak acid and weak base needed in order to make a buffer at a certain pH. So let's say you're asked to make a buffer at pH 7.95 and you already figured out that hypochlorous acid is the best weak acid to use to make a buffer at that pH because its pK is closest to that in terms of what you had available in the lab. So now you are going to make that. So let's do an example. It says calculate a volume of 0.9 molar hypochlorous acid and 1 molar potassium hypochlorite solution that must be combined in order to make a buffer at pH 7.95, and you're trying to make 100 ml of this buffer. So out of these solutions, you don't know how much to take. Do you take 50 ml of each? Do you take 40 ml of one, 60 ml of another? So how much do you take of each one of these? Well, what you're going to do is you're going to let x equal to volume of one of them. It doesn't matter which one. So we're going to let x equal to volume of, for example, 0.9 molar hypochlorous acid. And then 100 minus x would be the volume of its conjugate base. So remember, when you mix two liquids together, they're going to dilute one another. So you have to first take dilution into account. So the concentration of the weak acid in the buffer would be its initial concentration times its initial volume, which we let to be equal x, over total volume, which is 100. And the final concentration of potassium hypochlorite will be its initial concentration times the initial volume, which is 100 minus x, because the total must be 100, over the total volume. So when you mix two liquids, it's very important to take into account dilution. Now the rest is on the other side, so if you want, you can close your eyes so you don't get seasick when I move the camera, and I'll let you know when to open it. I have to do it this way so you guys can see the board a little better. Okay, you can open your eyes. All right, so we know that the weak acid is ionizing. Now, of course, it's going to ionize to a lesser extent because its weak conjugate base is present, so it's shifting that equilibrium that way. And Henderson-Hasselbalch equation works. So pH equals pK plus log of concentration of the weak base over weak acid. Again, you can use this method or you can use the icebox. They both work. If you use the Henderson-Hasselbalch equation, the pH is given, pK, the Ka of weak acids are given, you just look it up. So you put in the concentrations in terms of x. So in fact, now you have one equation with just one unknown, which is x. And so you can solve for x. So when you solve for x and you simplify it, and again, this is all just math, the step that usually students get confused is this step. How do you get rid of that log? So remember, that's 10 to the power of this. So that's where that 10 comes from. So 10 to the power of that equals this whole value. And so then the rest is easy, just solve. And so once you get x, since we let x equal to the volume of the acid, so that's the volume of our acid, and 100 minus x would be the volume of the conjugate base. You need to do something like this for experiment 4, part 2. So I'm going to assign you your pH values, and then you need to do a calculation similar to this on that one, on experiment 4. When you do experiment 4, again, you're going to dry lab it in this case. So I'll assign a value, and you'll do a similar problem like this on that experiment. Hopefully this was clear.